Hello and welcome to a little YouTube presentation on how to sketch the graphs of y equals sec x, y equals cosec x, and y equals cot x. Now this is probably the very first video you're watching on sec x, cosec x, and cot x. So before I draw the graphs, let's define what these new, weird and wonderful, magical trigonometric functions are. They're not mega complicated. They're actually, you get used to it. It just looks worse than it actually is, like a lot of trigonometry. Okay. Firstly, I'm going to define sec x. And sec x, weirdly enough, so can I just put, define here, yeah? So this is something you're going to meet. It's just a new name, basically, for a slightly different, a new function, which is the reciprocal of cos x, yeah? Sec x is going to be 1 over cos x. Cosec x, the one which you might have thought would be 1 over cos x, well, that's actually 1 over sine x. And this is just one of those situations in maths where it works the other way round from what you would think. Yeah, it's just the way it is. I think you'd have to go into the obscure language about what secant, cosecant, and cotangent really mean. But I don't know. I'll be honest with you. I really don't know why sec happens to be 1 over cos x and cosec happens to be 1 over sine x. But that's just the way it is. Finally, we've got the third function, cot x, and that's 1 over tan x. Yeah. So we've just got these new functions. They are literally the reciprocal trig functions. That's what all of them are. They are the reciprocal of a trig function. So sec x is the reciprocal of cos, cosec x is the reciprocal of sine, cot x is the reciprocal of tan. Now bear in mind that tan is sine over cos, and if we take the reciprocal of that, we're going to get cos x over sine x. So it's always worth remembering that cot x has two kind of things you can change it into. You can write cot x as 1 over tan x, but you can also write it as cos x over sine x. Yeah. So those are things to consider. Now, what I want to do next is basically just look at the graphs in this particular video. They're not impossible to draw, provided you're happy to kind of like, I don't like memorizing lots of stuff in maths, so I'm going to show you how we could deduce some of these. Let's think first about taking it in a slightly different order. Let's think about the graph y equals cosec x. And let's try and work out what it should look like. Now recall that cosec x is 1 over sine x, yeah? Okay, yeah, it works the other way around from what you might think. Now, let's say I didn't remember what this graph looked like, and you probably will remember something about its features when you go into the exam, but if they ask you to draw it, you're going to have to remember exactly what it looks like. And so it would be nice if you had a way to kind of work it out if you've forgotten. This is a way you can kind of work it out if you've forgotten. First, let's just draw the graph of normal sine x, yeah? Let's just draw the graph of y equals sine x, which looks something like that. I'm only going to draw it from 0 to 360 because that gives me the idea. And sorry, and minus 360 to 0 as well. So I'm just going to draw it from minus 360 up to 360. Let me put some values on there. Minus 360, minus 180, 180, and 360. Shall I do this in radians? Would you prefer radians or would you prefer degrees? I'll just write down the radian equivalent underneath, minus 2 pi, minus pi, pi, and 2 pi. You want to get more and more comfortable with using radians. In fact, I'm kind of disappointed that I actually wrote it in degrees now, but never mind. Let's put it out. Let's cross out the degrees. It's not that these functions only work in radians. They would work the same way in degrees. They're simply the reciprocal trig functions. They really are. Okay, so all I've drawn so far, and let's just put this in my key, I've drawn y equals sine x, which isn't what I'm trying to do. I'm trying to draw 1 over sine x. Okay, sine x achieves a value of 1 at pi over 2, yeah? So this is like pi 1 and minus 1. Sine x achieves a value of 1 at pi over 2. Well, can you see that if we're doing cosec x, when we're at pi over 2, we're going to do sine of pi over 2. That would give us 1, and 1 divided by 1 is 1. So it's definitely going to have the same coordinate as this curve here. And likewise, I could use the same argument for minus 3 pi over 2. And I could also use the same argument for minus pi over 2 and 3 pi over 2. Yeah. In other words, when sine x equals 1, 1 over sine x is going to be 1 as well. And when sine x equals minus 1, 1 divided by minus 1 is also minus 1. Okay. What about when we're doing sine of 0, yeah? Sine of 0, when x is 0, you get 0, yeah? Now, hopefully you recall, I certainly would mention this, I'm sure other maths teachers have mentioned this to you as well, that you get asymptotes where you're dividing by 0. Well, that means we're going to have an asymptote everywhere where sine x hits the x-axis, because we'll be doing 1 divided by 0, and the curve is not defined when you're doing 1 divided by 0. So we should have asymptotes at the points where, now let's just see if I can change the line style on this. I don't think I can actually. I'll just have to dot them. Yeah, so I'm going to do little dots. There's going to be asymptotes there. There's going to be asymptotes here because we're going to be dividing by 0. There's going to be asymptotes on the y-axis, so I just sort of dot over the y-axis there. And there's going to be asymptotes there. And there's going to be asymptotes at 2 pi there as well. Yeah, so it's got a lot of asymptotes, this curve, yeah? And you can actually think, well, what about when it's right next to 0? Well, as you know, sine x from small angle formulae, sine x is roughly equal to x. So we know that when x is really close to the y-axis, we're actually going to look very much like the curve 1 over x. Now, let me draw the curve which I'm trying to draw in red. And let me just move that y, because it's kind of in the way from where I'm drawing. I'll put it over there. Put the y, well, let's just leave the y. It's kind of in the way. It really is. So I'm not going to write it down for the moment. I'll put it at the end. But yeah, when sine x is really close to 0, you're basically doing the curve y equals 1 over x. And 1 over x starts looking something like this, yeah? And it's going to come down and hit that one there. And then we've got another asymptote over here. And that's because the curve's going to go up like that. And that's because as sine x gets smaller and smaller and smaller and smaller and smaller, you'll be doing 1 divided by a number getting smaller and smaller and smaller, and 1 divided by a very small number gets larger and larger and larger. And so you end up with cosec x looking like that in that first region where x is between 0 and pi. Now you can make exactly the same argument over here where cosec x is going to do something like that and just kiss at pi over 2, but otherwise it's going to be trapped between these two asymptotes. Same over here. It's going to do exactly the same thing there and then go back down. And same over here. It's going to come up, kiss the curve, and then go back up. Now, I've tried to do this on... I'm actually really quite happy with what I've done here. You may be looking at it thinking that looks like an awful mess. Maybe if I can zoom in a little bit, it might be a bit clearer. Yeah. The red curve is the curve I'm trying to draw. Cosec x is in red. Yeah, and the yellow curve is just normal sine x. I tell you what, let me show you what it looks like on a really good draft drawing package. This is sine x. Notice I am in radians here because, you know, it's 3.1415 quite clearly on that axis. I'm sure you can see that. And let's just get the whole curve in. There we go. Okay, so we've got a nice little, we got that almost all in. There we go. We've basically got, cool. Minus 2 pi up to 2 pi here. So I've drawn y equals sine x. Now, if I put in, I don't think it knows what cosec x is. So I'll do 1 divided by sine x. There we go. That's what it actually looks like. You can see you're getting asymptotes at minus 2 pi, minus pi, 0, pi and 2 pi, and it's because that's where sine x equals 0 at minus 2 pi, minus pi, 0, pi and 2 pi, and when you're doing 1 divided by 0 the curve is undefined. So yeah, I always describe cosec and sec x as kissing curves. Yeah, they kiss the original curves and then shoot up asymptotically where the original curve actually takes a value of 0, and that is what y equals cosec x looks like. Okay, cool. So that's cosec x. So what about sec x? Well, the great thing is because sine x is just a translation of cos x by 90 degrees or pi over 2 radians, exactly the same thing is going to apply to their reciprocal trig functions. It's not going to work any differently. So if I tell you what, I almost don't feel like, I feel like I should quit while I'm ahead and stop trying to draw these by hand on a graphics tablet very badly. If I was to do the same with Codex, the same argument applies basically. If I just get rid of these two, y equals cos x looks like this, yeah? And for y equals sec x, which is 1 over cos x, well, let's have a look. 1 divided by cos x, you get the kissing curve once again. It will be asymptotic at minus pi over 2, minus 3 pi over 2, because that's where cos x takes a value of 0, and also pi over 2, 3 pi over 2. I'll even put in a curve just to convince you that that's definitely the equation of the asymptote. Pi over 2. There we go. That is the equation of the asymptote. We normally dot asymptotes. That's what I like to do. I could do that on here. Line style. It's not really that interesting for you. You get the general idea anyway. So if I was drawing this myself in my notes, I would put dots there on the asymptote just so you can clearly see the asymptote. But just so we're clear, the blue line is y equals cos x. Is that green? The green line is y equals 1 over cos x. It might be red. I couldn't tell you really. I can't see colours. Okay, so that is sec x and cosec x. Now, that's why I say I don't really think you need to memorize those. I think tan x is much harder and cot x is much harder. I would suggest trying to just memorize this. One thing the way I memorize this one is I remember this, like tan of 90 minus x is actually 1 over tan x, and that's cot x. So I reckon I can use just this kind of principle to work out what the tan x graph should look like. What we're going to have to do basically is reflect it, because this is a function transformation. And by all means, just memorize these if you prefer. And it's a function transformation where first we're going to move the curve 90 degrees to the left, and then we're going to reflect it. So let's actually do that. In fact, let me write that down, because if you've ever got a function of ax plus b, quite strangely it feels at first, you need to translate b to the left, and then you need to stretch by a factor of a factor 1 over a. Yeah, and this is a similar thing really. First we're going to translate 90 degrees to the left, and then we're going to reflect the curve. If you change everything from x to minus x, and we're going to reflect the curve in the y-axis. Let's see if we can do that and generate the curve. So, and this is much harder. I very much doubt they'll ask this in the exam, because I think it's much harder to draw. And anybody who's artistically challenged, which is many people actually in mathematics, they would really struggle drawing the graph of cot x. But give it a go. It's a good challenge. Okay, so I'm going to draw normal tan x first. Normal tan x looks like this, from 90 to minus 90. And then we need to basically move it 90 degrees, shift it 90 degrees, and then reflect it in the y-axis. So shifting it 90 degrees to the left would suddenly make it go like this. That's shifted it 90 degrees to the left. Then we're going to reflect it in the y-axis, and so it's going to come down like this. So that is going to be the result if I can now rub off what I did before. So I'm building up the curve gradually using function transformations. Yeah. And then just like the original tan, it's going to repeat like wallpaper. Yeah. And so that would give us, by the way, that's actually hard to do. I suggest maybe it's easier with this one, just memorizing it, I guess, because then we're going to get a repeat like wallpaper. So we're going to have that going over there, And then if I can put the other line in green, the asymptotes in green, that would be nice just to keep it going. Yeah, it's really tricky to draw it. Let me just draw it on GeoGebra. This is a really handy graph drawing package, by the way. It's free. Yeah, anybody can get it. Just Google download GeoGebra. It's really good for this kind of stuff. So y equals cot x. Let's see if we got it right. Yeah, I think that's right. That's what we've got here. Yeah. So this one's going to have asymptotes at 0, at pi, at 2 pi. And that's because that's where tan x, the original tan x graph, was going through the origin, yeah, was hitting the x-axis. So once again, we've got that, because it's 1 divided by tan x, basically we're looking at where we're dividing by 0. Then we're going to have asymptotes. So we're going to have asymptotes there. We're going to have asymptotes at pi. We're going to have asymptotes at 2 pi, minus 2 pi, so on and so forth. It might be worth just memorizing that one. It's a tricky one to construct. It really is. The other two, you can kind of work it out. Okay, those are the graphs. After that, you can use function transformations, obviously, to transform these graphs, move them to the left, move them to the right, reflect them, stretch them, and so on and so forth. I'm looking at the exercise. The exercise question I'd like you to do on this is question 2, page 114 from exercise 6a. You're mainly doing sec and cosec in there. There's a couple of cot ones. Just bear in mind, you know, basically it's probably easiest on the cot graph to just memorize that it looks like that. Yeah, okay. Hopefully that's helped you just come to terms with these graphs. I'm going to do another video now on proving identities, then another one on solving equations. Hope that helped, and please do use the Maths Help Desk, which will be available in the lessons which I made clear on the Google Classroom. Yeah, just get in touch, basically. If you're stuck, get in touch and we can help. But yeah, the exercise to do for this is going to be exercise 6a, but there's 2 more videos coming to help you with exercise 6a. It will take you a couple of hours to work through 6a. It's quite a long exercise if memory serves. Okay, well done, thanks for listening, and I'll speak to you very soon.